Hey, in this tutorial we're looking at section 10.2 on discrete random variables. So random variable is represented by an uppercase letter, often it's usually x, and lowercase letters represent the associated probabilities. So for example, we've got the probability of capital X equaling lowercase x is interpreted as the probability that the random variable x will equal x. Okay, so capital X represents our random variable. X represents the values that random variable can take. Discrete random variables can only have integer values. So if we toss a coin 3 times and record the number of heads, then that would be an example of a discrete random variable. And in this example, we could say our uppercase X is equal to the numbers 0, 1, 2, or 3. If we look at a probability distribution, this defines the probability associated with each value the random variable can assume. So we're looking at this case again, of flipping a coin 3 times, and looking at the probabilities of getting 0, 1, 2 or 3 heads, and we're putting in a table like this, because the probability of getting no heads is 1 on 8, 1 head is 3 on 8, 2 heads is 3 on 8, and 3 heads is 1 on 8. And you can also represent them graphically, like this. We won't do that very often, but this is something that we'll work with a lot, our probability distributions. Now we should all understand from maths in about year 7 that the probability of any outcome has to be between 0 and 1. So 0, it can never happen. 1, it has to happen. And also if we add up all our probabilities, it will always equal 1. So for example here, 1 8 plus 3 8 plus 3 8 plus 1 8 equals 8 eighths or 1, as we know it must. A uniform distribution occurs when all possible outcomes are equally likely to occur. So that's, and a couple of examples for that is tossing a coin or rolling a dice. If we had a non-uniform distribution, that would mean that we might be flipping a biased coin or rolling a biased dice, something like that. So we'll have a look at a couple of worked examples. Now look, I haven't written down the actual worked example themselves because they're quite wordy, but we'll go through each step together. So a motorist travels along a main road in Brisbane. In doing so, they must travel through 3 intersections with traffic lights over a stretch of 2 kilometres. The probability that the motorist will have to stop because of a red light at any of the intersections is 2 on 5. Let X be the number of red lights encountered by the motorist. And by X we mean capital X, so we're saying that equals the number of red lights. So we're going through 3 red lights, traffic lights, sorry. So X could be equal, well, we could get no red lights, we could get 1 red light, 2 red light, or 3 red lights. Now for part A, so use a tree diagram to produce a sample space for this situation. So tree diagram. I'll try to fit it in, but we might start to get a little bit crowded here. So we can get red or we can get green for our first one. We can get red or green for our second set of lights. And we can get red or we can get green on our third set of traffic lights. And for all of these, the probability of getting a red light is 2 on 5, which means the probability of getting a green light is 3 on 5. And so forth. I won't worry about filling them all out. Now, a couple of things to note though, is that for my tree diagram you'll see that each time I've lined up my outcomes, it makes a lot more sense doing it like that. You see a lot of kids go along and they might curve around with their outcomes each time. Try to keep them all lined up, it just makes things a little bit clearer and a lot neater. Also, if you have a look at our branches here, if we add 2/5 and 3/5 together, you'll see that we get a whole. If we do the same thing with this, it'll happen and here, and here, and here, and here, and here. So our sample space then is that we could go along any one of our paths. So our one along the top is red, 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 and then we could go red, red, green, or we could go red, green, red, or we could go red, green, green, okay, or we could go our green, red, red, or our green, red, green, okay, or we could go green, green, red, or we could go green, green, green. So that would be our sample space. Okay, so part B is determine the probability of each outcome. Okay, so what we need to do is, for our red, for example, okay, that we go, our red, red, red would be 2/5 by 2/5 by 2/5. Our red, red, green would be 2/5 by 2/5 by 3/5. Okay, so it'd be a little bit different each time. So what I'm going to do is I'm just going to write them down near it. Okay, they're all in your textbook. I'm not going to go through the calculation. Red, red, red becomes 8 on 125. Okay, red, red, green is our 12 on 125. Our red, green, red is also 12 on 125. Okay, our red, green, green is 18 on 125. Our green, red, red is our 12 on 125 again. Our green, red, green is 18 on 125. Okay, our green, green, red is also 18 on 125. And our green, green, green is 27 on 125. Okay, so they're just our probabilities associated with each one. Okay. Part C is find the probability distribution for this random variable. Okay, so our probability distribution, okay, what we need to do then is set up our table and say, well, we've got x, and we know x can be 0, 1, 2, or 3 for our red lights, and we've got the probability that x equals x. Okay, so we look and go, what's the probability that we get no red lights? Well, we know that. That's our green, 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 which is our 27 on 125. Okay, when we look at getting one red light, okay, well that is our red, green, green, okay, or our green, red, green, or our green, green, red. So it'll be 18, 18, and 18, which is 54 on 125. Okay. If we have a look at two red lights, well, it's red, red, green, red, green, red, okay, or green, red, red. Okay, when we add those together, we get 36 on 125, and our three red lights is simply our 8 on 125. Okay, so that's our probability distribution. Okay, so part D is test whether this probability distribution obeys the necessary properties for a discrete random variable distribution. By that, basically it means if we add all these up, does it equal 1? Okay, and the answer is yes. Okay, if we add up all our probabilities, it does equal 1. Okay, and that's the end of that worked example. Okay, so I'm not having a look at worked example 2, that one's pretty straightforward. Okay, so you can have a look at that one yourself. Okay, we are having a look, however, at worked example 3. So, a coin is biased, so that there is twice as many chances of it landing with heads up. The coin is tossed 3 times. Okay, so list the sample space and calculate the associated probabilities for each of the possible outcomes. Okay, well, we've got, okay, if we're tossing the coin 3 times, well, we can go head, head, head. We can go head, head, tail. And go head, tail, head, or head, tail, tail. Okay, or we can go our tail, head, head, or our tail, head, tail. We can go tail, head, head, or we could go tail, so that should be tail, tail, head. Or we can go tail, tail, tail. Okay, there are options. Okay, now we're going to work out, okay, what the probability of each one of these is occurring. Okay, so our head is twice as likely to come up as our tail. That means the probability of getting a head is going to be 2 on 3, while the probability of getting a tail is going to be 1 on 3. So probability of getting 3 heads is going to be 2 on 3 by 2 on 3 by 2 on 3, okay, which equals our 8 on 27. Okay, if we go through this process with all of these, we find that our head, tail is our 4 on 27. Our head, tail, head is also 4 on 27. Our head, tail, tail is 2 on 27. Our tail, head, head is 4 on 27. Our tail, head, tail is 2 on 27. Our tail, tail, head is 2 on 27. And our tail, tail, tail is 1 on 27. Okay? Part B is find the probability distribution for this non-uniform distribution. Okay, so again we've got to set up our table. Okay, so we can say that we've got our x. Again, we know we can get 0, 1, 2, 3 heads. Okay. And then we're saying, well, the probability that x equals x, okay, is, so getting no heads, okay, well that's just our tails, 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 so that's 1 on 27. Getting 1 head, well that's our tail, tail, head, tail, or head, tail, tail. So we add those together, okay, and we simplify our fraction to 2 on 9 when we do that. Our 2 heads, well that'll be this one, and this one. Add them together, we get 4 ninths. And getting our 3 heads is our one up here, which is our 8 on 27. Okay. And then we want to find, the last part is find the probability, okay, that x is greater than 1. Okay, well to do that, okay, we go, well it's greater than, not greater than or equal to, so it's got to be that it's 2 or 3. Okay, so that means that we've got 4 on 9 plus 8 on 27, which is equal to 20 on 27. Okay, and that's all there is to it for this section. So look, to be honest, most of this should be revision. Okay, so hopefully you don't have too much trouble getting through the questions.